When a backyard telescope outshines billion-dollar space gear, you can't help but notice. And when it catches something the pros either can't see or don't want to talk about, curiosity turns into real questions. Now, if we're talking about an object from outside our solar system, something that's been drifting through the dark for millions of years before landing in our patch of sky, those questions don't just simmer, they boil over. That's exactly what happened on a crisp November night in 2025. Paul Craigs, an astrophotographer with a Dwarf 3 telescope, aimed his lens at a fast-moving dot called 3I Atlas. He figured he'd get the usual, a messy blur, a fuzzy cloud, what you expect from a comet. Instead, his screen showed something nobody was ready for. There it was, sharp edges, a bright white center, a strange blue glow coiling around it, almost like energy or exhaust, like it was designed on purpose. Not the disorderly, crumbling ball of ice we're told to expect. This thing looked controlled, intentional, all wrong, and that's exactly what made it feel right. Within hours, the photo exploded across amateur astronomy forums. People stared, speechless. From home offices and backyard setups in Arizona to city rooftops in New York, old hands and brand new stargazers felt that jolt. The shock you get when you see something that just shouldn't exist, not if you believe what you've always been taught. Right away, some folks called it fake, blamed it on software tricks or camera glitches. And honestly, they weren't out of line. Modern astrophotography is complicated. You shoot raw frames, grainy, almost empty. Then you stack them, stretch the limits, sharpen the details. Every step means making choices, and every choice changes the final picture. Critics said Paul pushed the processing too far, turned noise into structure, made up those sharp edges and that blue glow. But then more images started rolling in. Different people, different telescopes, different cameras and software scattered all over the world. The pictures weren't identical, but the core was the same. This object looked sharper and more solid than anything the official feeds from Hubble or the big observatories had shown. A woman in California, working with a cheap refractor, caught something similar. A club in Texas pooled their gear and nailed down a crisp core, too neat for a comet falling apart. Even folks in Europe dealing with lousy skis squeezed out glimpses of structure when they really pushed their data. It wasn't just one guy, not just one telescope, not just one editing trick. This was a pattern, and in science, patterns matter. One outlier, easy to ignore, two, maybe a fluke. But when dozens of independent people, all using different tools and methods, land on the same weird result, you have to pay attention. This wasn't groupthink. Nobody was in cahoots. They just pointed their scopes at the same thing and reported what they saw. And what they saw didn't match the safe story. That 3I Atlas was just another interstellar comet, oddball chemistry maybe, but nothing special about the shape. Excitement crackled through the community, along with a touch of unease, because this wasn't just any comet. This was an interstellar visitor, only the third ever confirmed from beyond our solar system. And if these images are real, if this is what 3I Atlas actually looks like when you strip away the official gloss, then maybe we're missing something big. The real question isn't just what 3I Atlas is, but why does it look so different depending on who's capturing it and how? That gap, the space between what the pros see and what backyard astronomers find, is where this story really begins. Because sometimes, the biggest discoveries don't come from labs with endless funding. Sometimes, they start with someone in their backyard, pointing a telescope at the sky, and catching something nobody was ever supposed to see. Paul Craigs isn't some conspiracy nut out to take down NASA. He's an experienced astrophotographer, someone who's spent years pointing his telescope at the night sky, chasing down distant galaxies and faint nebulae. His gear, a Dwarf 3 telescope. It's decent, nothing fancy, nothing that'll blow your mind with its specs. Frankly, it's about as expensive as a used car. This is the kind of setup a dedicated hobbyist would own, the folks who give up sleep to track asteroids and snap pictures of comets from their backyard. Not Hubble level, not James Webb, not even close. Those big observatories float above Earth, cost fortunes, and can pick up the faintest light. Craig's telescope sits in his yard. Yet somehow, this modest rig caught something the billion-dollar instruments either missed or just left out of their official images. That's the weird part. That's what makes you stop and think. How did a backyard scope see something so different from what the world's best telescope showed us? Craig's posted his photo online. It's not subtle. You don't have to squint or guess at what you're seeing. There's a clear shape where you'd expect a blur. There are edges, a bright white core that looks almost like a fuselage, and this strange blue glow wrapping around it. The blue isn't scattered sunlight bouncing off ice. It looks more like something glowing from within. It looks active, switched on. Now, comets are supposed to be messy. They're frozen clumps of rock and ice, barely held together, and when they get close to the sun, they start shedding gas and dust. That's what creates the coma, a fuzzy, expanding cloud that hides the solid core. Usually from Earth, all we see is a blur, a fuzzy ball with a tail streaming away from the sun. That's the model. That's what comets do. That's what everyone expects. Three-Eye Atlas, at least in Craig's image, isn't following the rules. It's not a smudge. It's crisp with real boundaries. It almost looks built, which is the kind of thought that makes scientists nervous for good reason. If this photo is real, if this is what's actually out there, then it just doesn't fit the comet template. And if it's not a comet, then what is it? The internet went wild. People in amateur astronomy groups, oddball science forums, even mainstream science channels started talking. Some folks applauded Craig's for his skill. Others accused him of faking the whole thing, over-processing, adding filters, pulling out details that weren't really there. A few more knowledgeable voices chimed in, saying, look, astrophotography is tricky. You stack lots of pictures to cut down the noise. You tweak the details, adjust curves, try to bring out the faint stuff. Every adjustment you make changes how the final image looks. So the real question wasn't if the image was processed. Every astrophoto is. It's whether the processing revealed something real or just created an illusion out of noise. That's a fair question. It's exactly what scientists ask when they look at any kind of data. But here, where it gets interesting, other people started sharing their own photos, different telescopes, different locations, different ways of processing the images. And yet, the same basic thing kept showing up. This object looked sharper, more defined than anything the official releases from Hubble or the other big telescopes had shown. It wasn't just Craig's. It wasn't just his telescope. It started to look like a pattern, a real one. And when patterns show up, you have to pay attention. If you want to know why Three-Eye Atlas matters, you've got to start with where it comes from, and really, with what came before it. In astronomy, the code names tell the whole story. Three-Eye just means it's the third interstellar object ever found. The first was 1I/Oumuamua, which showed up in October 2017 thanks to the Pan-SDARRS telescope in Hawaii. The name Oumuamua was a perfect fit. It's Hawaiian for scout or messenger, and that's exactly what it felt like. A visitor from somewhere else, totally unfamiliar. Right from the start, Oumuamua was weird. Its path through the solar system was a dead giveaway, moving way too fast to be trapped by the sun's gravity, shooting in from Lyra and out toward Pegasus. But that was just the beginning. Shape-wise, it was a real oddball, maybe 10 times longer than it was wide, spinning in this chaotic, tumbling way every 7.3 hours. Its brightness jumped all over the place, which hinted at a super stretched out or maybe pancake-flat form, but honestly, nobody snapped a clear picture. The surface reflected a lot of light, much more than your average asteroid or comet, and it had this reddish tint, probably from a long soak in cosmic radiation. But then things got even stranger. As it zipped away from the sun, it sped up, just a little, but enough that gravity couldn't account for it. And yet, there was nothing coming off it. No gas, no tail, no hint of water vapor, carbon dioxide, or any of the usual stuff you'd see if the sun was heating up a comet. The acceleration was real. Measured again and again, but nobody could explain what was causing it. Normally, comets pick up speed when gas jets shoot out, basically a rocket effect. But Oumuamua wasn't giving off anything you could see. Astronomers started arguing, loudly. Some insisted there had to be outgassing, maybe too faint or too quick for our telescopes to catch, possibly from weird ices like hydrogen or nitrogen that vanish without a trace. Others thought maybe it was just a rocky asteroid, and the push came from sunlight heating one side and causing a tiny but steady nudge solar radiation pressure. But then Avi Loeb from Harvard threw in a wild card. What if Oumuamua was made, not born? He suggested it might be a light sail, a thin, shiny structure built by aliens, using starlight to cruise through space. It's not a crazy idea. We've built and tested light sails ourselves. Something thin and reflective could speed up under sunlight without shedding any gas. The shape, the reflectivity, the weird acceleration, they all fit. But there's a canyon of difference between could be and is, and the evidence just wasn't there. Most scientists stuck to natural explanations, even if none of them fit perfectly. Still, the debate didn't die down. Oumuamua drifted away, too faint to see anymore, taking its secrets with it. We're still arguing about what it was. Then came 2I/Borisov, spotted in August 2019 by Gennady Borisov, an amateur astronomer with his own homemade telescope in Crimea. Where Oumuamua was bizarre, Borisov was textbook. It had a visible coma right away. You could see gas pouring off as it warmed up, and the spectra showed water vapor, carbon monoxide, pretty much what you'd expect from a classic comet. As it neared the sun, it grew a tail. In every way, Borisov acted like the comets we know from our own solar system. Scientists, honestly, breathed a sigh of relief. Borisov seemed to prove that most interstellar objects are just regular comets from other stars, chunks of ice and rock kicked out during planet formation, drifting for ages until they wander into a new solar system. Borisov made the universe feel a little more familiar again. It was a reminder that, sure, space is full of surprises, but not everything out there is totally alien. But even Borisov had its quirks. Its coma didn't act like those of the usual solar system comets. Polarization was off, pointing to dust grains that just weren't the same as what we'd expect. There was more carbon monoxide too, way more than you find in local comets. That hinted Borisov formed somewhere colder, farther from its own star. And while we never got a direct look at its nucleus, it seemed to be crumbling, dropping pieces as it swung past the sun. That fits what comets do, but it made you wonder if it was barely holding together. Still, Borisov felt familiar. It lined up with the models, ticked all the boxes. It was the interstellar comet folks had expected to see. Then along came 3I Atlas, and honestly, it's more unsettling than Oumuamua, even though on the surface it looks more like a classic comet. Sure, it has a coma and shows the usual activity, but the details are wild. The chemistry, way out there. The polarimetric data, nobody's seen anything like it. And that amateur photo, there's structure in the coma that doesn't match the messy, breaking apart look you'd expect from a comet under stress. It's almost as if 3I Atlas took notes from Oumuamua and Borisov, blending just enough normal to seem plausible but throwing in new oddities to keep astronomers guessing. At first, it looked routine. But once people nailed down its orbit, the truth came out. It's moving way too fast to be from around here. The path is hyperbolic, straight in from interstellar space, through our solar system, and then gone again off into the galaxy. This isn't some leftover chunk from our neighborhood. It's a visitor from another star system, a place where planets might have formed differently, where the chemistry and heat history could be nothing like what we know. That alone makes it a big deal. And the weirdness just keeps piling up. Right from the start, every big observatory with a clear shot at the sky started tracking 3I Atlas. That's just what happens with interstellar objects. They're so rare, so packed with scientific potential, that when one shows up, everyone drops what they're doing. Hubble spun around and made room in its packed schedule. The James Webb Space Telescope, with its incredible infrared eyes, locked on and started scanning for molecules. Ground-based telescopes everywhere, Keck in Hawaii, the very large telescope in Chile, all sorts of observatories across the US and Europe, coordinated to grab whatever data they could. Even a few spacecraft in orbit around Mars and probes watching the sun chipped in, squeezing in observations whenever possible. This wasn't just a big deal. It was a solar system-wide science event, the kind of all-hands-on-deck moment that only happens for something truly extraordinary. The official data says 3I Atlas looks like a comet, at least if you don't look too closely. Hubble saw a bright, compact nucleus wrapped in a coma, that classic cloud of gas and dust that forms when sunlight boils ice off a comet's surface. The coma looked mostly round, but with some odd patches that might be jets or spinning active spots. Astronomers even spotted the start of a tail, or maybe more than one, a thin streamer of gas and dust pushed away by sunlight and the solar wind. It wasn't dramatic, not the sweeping light show most people picture. The tail was faint, subtle, really only visible after some heavy image processing. Still, it was there. It acted like a tail should, pointing away from the sun, shifting as the comet moved along its path. When astronomers pointed their spectrographs at 3I Atlas, they broke its light into a rainbow and found the usual suspects. Water vapor turned up in the ultraviolet, thanks to the telltale emissions from hydroxyl radicals, those fragments left behind when sunlight rips water molecules apart. Carbon dioxide stood out in the infrared, glowing at wavelengths that matched the way sunlight shakes its molecules. Carbon monoxide showed up too, along with faint hints of more exotic stuff like carbonyl sulfide and maybe even some bigger, more complex organics. Dust grains scattered visible light, filling in the spectrum with a smooth glow. That helped researchers figure out how much solid stuff was swirling around the comet and how big those grains were. By every standard test astronomers use, 3I Atlas checked all the boxes. The chemistry was odd. Carbon dioxide dominated, way more than usual, but not impossible. It just meant this comet grew up somewhere else under different rules. The data was solid, the outgassing was real, the tail was real. Everything pointed to a classic comet, ice and rock, heated by the sun, falling apart as it sped through our neighborhood. But there were still puzzles. The size of the nucleus. No one could pin it down. Estimates ranged from just under half a kilometer to over 5 kilometers across. That's a huge spread. The problem? The nucleus hides inside the coma, a shroud of gas and dust that makes it nearly impossible to tell where the solid part ends and the fuzzy cloud begins. When astronomers measure brightness, they see both blended together, and separating them means making educated guesses about how reflective, active, or icy the comet really is. Get those wrong, and your size estimate flies out the window. The composition is where things get really weird. The James Webb Space Telescope aimed its infrared eyes at 3I Atlas and saw something surprising. Carbon dioxide, not water, ran the show. The ratio of carbon dioxide to water was off the charts, higher than pretty much any comet in our solar system. That alone set 3I Atlas apart. Sure, there was still water, ice, and carbon monoxide, plus carbonyl sulfide and dust. But carbon dioxide dominated, which doesn't happen with homegrown comets. Usually, comets are water-rich because they formed where water ice was everywhere. Not this one. 3I Atlas came from another star system, shaped by conditions we can only imagine. Ultraviolet observations added another twist. Even when the comet was more than 3 times farther from the sun than Earth, it was still venting water vapor. Telescopes picked up hydroxyl emissions, the signature of water molecules splitting apart in sunlight. Comets usually go quiet that far out, but 3I Atlas stayed active. Maybe its ice vaporizes at lower temperatures, or maybe the way it's built just makes it more excitable. So here, where things stand, 3I Atlas acts like a comet, just one from another solar system. The experts, NASA, top research teams are all on record. There's zero real evidence for anything artificial or engineered here. No weird signals, no unexplained accelerations, no odd structures. It's a comet, period. Still, it doesn't play by the usual rules. The wild carbon dioxide levels, the mystery about its size, the unexpected activity, they all push the limits of what we're used to seeing. The comet isn't breaking the laws of physics, but it's definitely stretching them. And that brings us to Paul Craig's backyard photo. If this is just a comet, then why does it look so different through his telescope? Why are the professional images all fuzzy and diffuse, while the amateur shot pops with sharp structure? Is it just a trick of image processing, some artifact? Or is there something about how we're observing this thing, something in our instruments or our assumptions, that's making us miss part of the picture? That's the real question. These odd details, the little things that don't add up, are what make even the most skeptical scientists stop and wonder if just maybe we're looking at something we've never seen before. There's a certain kind of tension that sneaks up on astronomers when their instruments spit out results that just won't line up with what's supposed to happen. It's not panic, not exactly. It's not really excitement either. It's more like a stubborn, nagging itch. This sense that maybe the whole framework is missing something big. That's what 3I Atlas has been stirring up ever since those first close observations hit the desks. Sure, the measurements say it's a comet, but there's a laundry list of weirdness in the data that just doesn't fit the usual picture. These aren't wild claims from the fringe. They're hard numbers from reliable instruments, published by scientists who'd rather stay grounded than chase headlines. Still, the findings are odd. Let's start with the strangest bit, the polarimetric signature. Polarimetry sounds complicated, but it's really just a way of looking at how light gets twisted around when it bounces off dust or ice. Normally, when sunlight hits a comet's coma, some of that light comes away polarized, and by measuring that, scientists can figure out what the dust is like, how big the particles are, what they're made of, whether they're fluffy or compact. And with comets, there's a typical pattern. At smaller angles between the sun, the comet, and us, the polarization goes negative. As the angle grows, it flips positive. This is the negative polarization branch, and people have it down to a science. But 3I Atlas, it threw out the rulebook. A recent study, done before it swung closest to the sun, showed a negative polarization branch that's both deeper and tighter than anything people have ever seen in a comet or asteroid. We're talking about polarization hitting minus 2.7% at small angles, flipping at around 17 degrees. Okay, numbers aside, here what matters. The way light bounces off this thing is like nothing else out there. It doesn't match any known comet, not even close. It doesn't fit with asteroids either. The only real takeaway is that the surface, or maybe the coma, or both, are made of stuff, or shaped in ways we've never cataloged before. So what's going on? Maybe the dust is unusually tiny or shaped in some weird way. Maybe the surface has a strange texture or mix of stuff that scatters light differently. Or, and this is where things get really speculative, maybe something happened out there. Some process we don't even understand yet. Changed the outer layer in a way no solar system comet has ever experienced. Whatever the reason, the polarimetric data is basically a giant red flag. Something about this object is off. And then there's the matter of what it's made of. We already talked about this, but it's worth repeating. The carbon dioxide to water ratio is off the charts. In our solar system, comets usually have water as the main ingredient, with carbon dioxide as an afterthought. 3I Atlas turns that upside down. Carbon dioxide takes over. The James Webb Space Telescope laid this out in plain infrared. That's not just quirky, it's a huge clue. It says this comet formed somewhere very different, maybe where water ice just wasn't around, or where carbon dioxide stuck around better, or maybe the whole system's history was just wildly different. 3I Atlas is living proof that not every star system cooks up comets the same way. Now, toss in the uncertainty about size and mass, and things get even messier. We don't actually know how big the nucleus is, so we can't really say how much gas and dust it should be pumping out when the sun hits it. If it's small, say, about 440 meters across, then the amount of outgassing we see is wild. The surface would have to be hyperactive, losing ice at rates that almost defy physics for something just sitting in the sunlight. If it's bigger, 5 or 6 kilometers, then the numbers start to make more sense, but we lose that crucial constraint that could help us figure out what it's made of and how it's built. So this isn't just a little hiccup. The uncertainty actually opens the door to all kinds of other ways to explain what's making 3I Atlas tick. And that keeps astronomers up at night, wondering what else we might be missing. Let's talk about the weird shapes and behaviors we see in the coma and tail. Some of this comes from big observatories. Some comes from dedicated amateur astronomers out in the dark with their own gear. And what keeps showing up is that these tails aren't just a simple streak behind the comet. Instead, people see all sorts of structures, multiple jets spraying out, jets that aren't even lined up the same way from night to night, and every now and then, something called an anti-tail. That's when a feature seems to point toward the sun instead of away from it. Comets can do this, sure. Stuff like the angle we're looking from or the size of the dust grains can mess with the view. Solar radiation pushes different particles in different ways, and that can explain some of the weirdness. But here, it's more than that. The jets blink on and off. The shape of the tail shifts. Even the comet's brightness goes up and down in ways that don't fit the simple ice turns to gas story. And that brings us to the big question. Where's all this energy coming from? If the nucleus is as small as some data says, but the outgassing is as wild as it looks, something doesn't add up. Sublimation, ice turning straight into gas, takes heat, and that heat comes from the sun. But when you crunch the numbers, the sunlight hitting the comet doesn't seem like enough to account for the show we're seeing. Sure, maybe the surface is darker than we thought, soaking up more heat. Or maybe there are hidden pockets of gas trapped inside, popping open and venting suddenly. Or the comet spins just right, flashing fresh ice at the sun at key moments. All of these could work in theory, but at some point you're just stacking excuses, bending the model to fit what's already happened. And after a while you have to wonder, are we actually explaining the comet or just patching holes? There's another wrinkle. 3I Atlas swung closest to the sun perihelion in late October 2025. But from Earth, the comet was lost in the sun's glare. We missed the main event. No continuous data, no clear look at what happened when the comet should have been at its wildest. That gap is a black box. Who knows what went down during that time? Maybe it broke apart and came together again. Maybe it dumped a pile of material all at once. Maybe it just cruised along, same as ever. We honestly don't know. And when you don't know, it's easy for speculation to creep in. So here's the reality. Nothing here proves anything wild, like 3I Atlas being artificial or built by someone. But at the same time, it's not just another boring comet. Not even close. The strange polarization, the weird carbon dioxide readings, the size problems, the shifting jets, the puzzling energy budget, they're all real observations from solid sources. They poke holes in the idea that this is just another rock ice ball passing through. They signal that something stranger is going on, and they force us to look harder. They're not proof of anything exotic, but they're not nothing either. They push us toward a new hypothesis. Maybe 3I Atlas is a comet that's been changed, reworked by its own long trip through space. And here's a way to make sense of it, all without jumping off the deep end into wild theories. Think about galactic cosmic rays. These things are everywhere, high-speed particles, mostly protons and atomic nuclei, zipping through the galaxy at nearly light speed. They don't care what's in their way. For an object like 3I Atlas, which probably spent millions, maybe billions of years drifting between stars, cosmic rays aren't just background noise. They're relentless. They change things. Planetary scientists have run the models and found that comets out in interstellar space get hammered by these rays over and over in a process called cosmic ray processing. Picture it, a comet nucleus, frozen and ancient, just floating in the dark. Cosmic rays slam into it, digging in, breaking chemical bonds, rearranging molecules, making simple stuff into complex compounds. Carbon monoxide turns into carbon dioxide. Organics form. Water ice gets altered or even destroyed. After long enough, you end up with a crust, a tough, chemically warped skin, shaped more by radiation than by heat or collisions. It's not the same comet that left its home system long ago. It's been changed by its journey, processed by the galaxy itself. This isn't just a guess. We know cosmic rays have these effects because we see the same thing happening to stuff right here in our solar system. Look at the Kuiper Belt. Those distant, icy worlds show clear signs of radiation messing with their surfaces. Meteorites that have spent time drifting in space come back with scars from cosmic ray hits. The physics, solid. What's new is realizing that interstellar objects, ones that have wandered through the galaxy for ages, moving way faster than anything local, get hit by cosmic rays on a whole different level. So by the time 3I Atlas showed up in our solar system, its surface layers probably weren't anything like what they started as. They've been baked by radiation for who knows how long. And honestly, that fits the data weirdly well. Take the crazy high carbon dioxide compared to water in its coma. Cosmic rays could have turned carbon monoxide ices into carbon dioxide over millions of years. The deep red color we see in its spectrum, that's a classic sign of complex organic molecules, likely built up by endless particle bombardment. Even the odd way its dust and ice scatter light, nothing like solar system comets, could be from textures and compositions that only form after this much radiation. Right now, the models say the stuff pouring off 3I Atlas is coming from just the top 15 or 20 meters of this altered crust. That matters. We aren't seeing the untouched ice from the comet's birthplace. We're seeing what's left after eons of cosmic weather. The deeper layers, they could be totally different. Maybe more water, maybe different isotopes. But unless we find a way to dig down or the comet cracks open on its own, we'll never know. And that changes things. If cosmic ray processing is standard for interstellar objects, then every comet we catch from out there is a survivor, not a true sample of another star system's building blocks. It's like digging up an ancient artifact. Sure, it's real, but its surface has been changed by centuries underground. That's 3I Atlas. The comet we're looking at now probably tells us more about the journey through interstellar space than about the place it was born. That brings up an interesting idea. Maybe these interstellar comets are their own thing. Not classic comets, not asteroids, but a new class shaped by their time drifting between stars. If that's true, we need new ways to think about them and new models to guess what they'll do. We might even have to rethink what we learned from 1I/Oumuamua and 2I/Borisov. Maybe the reason they looked so different is that they'd each been processed by cosmic rays, just to different degrees. Still, the cosmic ray theory doesn't answer everything. For instance, if 3I Atlas's outer layers are so battered and weakened, why hasn't it fallen apart? Comets break all the time, especially after a close brush with the sun. Yet 3I Atlas is still hanging together. That hints its core is tougher than we thought, or maybe there's something about its insides that gives it extra strength. Either way, there's still a lot we don't know. Jets and outgassing asymmetry, they're a real puzzle. Sure, cosmic rays can mess with the outer layers, maybe change what's in them, but that doesn't really clear up why the outgassing is so wild, or why those jets keep shifting. That kind of action points to something more alive inside the comet. Maybe there are pockets of frozen stuff under the surface that suddenly get exposed, or maybe it's just active patches spinning around as the comet rotates. The cosmic ray idea is useful for explaining what the comet's made of, but it doesn't give us the full picture. We still need to get a better grip on how the nucleus is built and how it moves. So where does that leave us? The cosmic ray processing model lands somewhere between the boring and the outrageous. It says 3I Atlas isn't just another plain comet, but it's not an alien spaceship either. It's something in between, something we haven't really seen before. It's a messenger, not just from another solar system, but from the strange, empty space between the stars. That's pretty exciting, honestly. It's worth digging into, even if it's just our best guess for now. And like all science, it's open to change. As 3I Atlas keeps moving away and we collect more data, we'll either cement this model or blow it apart. Either way, we're watching something genuinely new live as it happens. Now let's circle back to that backyard photo, the one that got this whole conversation going, because it's time to tackle the big question head on. Why does Paul Craig's telescope pick up structure but the pros just get a blur? Is he seeing something real, or is it just an artifact? And if it is real, what does that say about the comet, or maybe about how we look at the universe in the first place? Honestly, pros and amateurs seeing different things isn't that rare in astronomy. It happens more than you'd think, usually without all the drama. The history of astronomy is full of stories where amateurs spotted details the pros missed, or made discoveries that flipped our understanding of the universe. Take Comet Shoemaker-Levy 9. When it smashed into Jupiter in 1994, the pros were ready. They had predictions, fancy equipment, the works. But some of the most unforgettable images came from amateurs all over the world who caught details the big telescopes missed because of strict schedules or rigid data processing. Or think about supernova hunters. Amateurs have found hundreds of exploding stars by just scanning galaxies night after night, often getting there before the automated surveys. The point is, pros and amateurs play by different rules and bring different strengths. Professionals have the big instruments and deep technical know-how, but they're also tied up in institutional routines that can be slow to change. They follow established protocols, and sometimes that means they focus on data that fits what they expect, not data that challenges them. Professional telescopes, especially the space-based giants like Hubble, are built for specific jobs. Hubble's amazing at picking out faint stuff way out at the edge of the universe, measuring the chemistry and movement of distant galaxies, or catching fine details in nebulae. It takes long exposures, sometimes hours, to catch things so dim we'd never see them otherwise. The filters target exact wavelengths, picking up the signatures of hydrogen, oxygen, and other elements. Then the data goes through processing designed to pull out certain kinds of information, like redshifts or spectral lines, at the scale of whole galaxies or clusters. So, when Hubble looks at a comet, it gives you great data about how bright the coma is and what it's made of. You get the total light from the whole thing, and detailed spectra that tell you which molecules are there and how much of each. But here's the catch. Hubble's pipeline isn't set up to sharpen the details of the nucleus itself. It's built to measure chemistry, not to draw sharp boundaries. The images you get from Hubble are tuned for scientific measurements, not for showing crisp structure. That's just how the system works. Amateur astronomers working from the ground face a whole different set of challenges. Their telescopes are smaller, sometimes just a few inches across, nothing like Hubble's massive 8-foot mirror. And then there's the atmosphere, always shimmering and shifting, blurring the view as air currents dance across the lens. But here's the thing. Modern amateur gear is surprisingly advanced now. With electronic tracking, these scopes can lock onto a moving object and keep it dead center for hours, barely drifting at all. The latest CMOS and CCD cameras can snap hundreds of quick exposures, stacking them to tease out faint details and cancel out noise from both the air and the detectors. What really sets amateurs apart, though, is the freedom they have in processing. They're not following a set script or some institutional checklist. They can decide which colors to highlight, how much to sharpen, how far to push the contrast. They can tinker, try a dozen different methods, and see what pops out. It's creative, sometimes even a little wild. But here's the tricky part. When you see new features emerging after all that processing, are those details really there, hidden in the data all along? Or is the processing itself inventing patterns that don't truly exist? That's a tough call. In theory, you could take Hubble's raw data and process it just like Craig did with his amateur images. Same sharpening, same contrast tweaks. If you still end up with a blurry smudge, then maybe Craig's structure is just a processing artifact. But if Hubble's data starts showing the same features, then maybe those details were there all along, just buried by the usual professional methods. As far as I know, nobody's done this head-to-head comparison in public. The raw Hubble data for 3I Atlas is out there, and someone with the right skills could bring amateur-style techniques to it. But to really settle things, you need someone fluent in both the pro and amateur worlds, and you need to lay out every step for all to see. Without that, we're stuck with conflicting images, with no obvious way to say which one tells the real story. So the contradiction remains. The professionals show us a classic comet, fuzzy, diffuse, with a coma swirling around it. Some amateur shots, though, look sharper, with odd structures standing out. Both sets of images are real, captured by actual telescopes pointed at the same object, but they tell different stories. One says, here's a normal interstellar comet, odd maybe, but still just a comet. The other hints at something more structure that doesn't quite fit, something strange enough to make you look twice. Which story wins? Maybe both are partly true. Maybe the answer's somewhere in the middle. Maybe the real point here is that observing isn't just about collecting light. about how we interpret what we see, shaped by our tools, our habits, and the questions we're bold enough to ask. There's another side to all this, and it's the sort of thing that makes scientists uneasy. What if the pros aren't really wrong, just not seeing the whole picture? What if the ways we've studied comets for decades, methods that work perfectly for solar system stuff, just aren't enough for interstellar visitors? Think about it. We've watched hundreds of solar system comets. We know their usual mix of ices and dust, how they shed material, what sorts of shapes and tails to expect. Our equipment and techniques are tuned to pull out exactly that kind of information: brightness, spectra, size, tail shape. The whole field is built on that template, but interstellar comets, they're wild cards, born elsewhere, battered by cosmic rays, carrying who knows what inside. Their chemistry and structure might not match anything we're used to. If you come at them with the same assumptions and tools you use for local comets, you could miss something big. Maybe you blur out interesting structure because you're expecting a featureless fuzz. Maybe you dismiss weirdness as noise because you expect things to look tidy and symmetrical. The way we look shapes what we actually see. Amateur astronomers come at this with a different mindset. They're not tangled up in theories or trying to make the data fit some big picture. Mostly, they just want to capture what's actually there as clearly as possible. That kind of freedom, just looking, not following a set playbook, sometimes lets them spot things the pros overlook. It's not that amateurs are sharper or more skilled. They just ask other questions and try different methods. Every so often, that's exactly what shakes up the usual story. There's no plot or cover-up here. This is just how science moves forward. Institutions figure out methods that work well for certain problems, and those ways of doing things become the standard. But once in a while, something pops up that doesn't fit, and the big institutions need time to catch up. In the meantime, people outside the system, using their own tools and ideas, might notice something first. That's probably what's happening with 3i Atlas right now. The professionals collect hard, careful data. The amateurs turn up surprises. You need both. Neither group has the whole answer on their own. So what do we do when the data doesn't line up, when nobody agrees on what we're really seeing? We keep going. We watch. We gather more evidence. We tweak our models and test them. Most important, we stay open to the idea that this object might not fit into any tidy box we've built so far. 3i Atlas isn't waiting for us. It's out there moving through the solar system, and every astronomer chasing it knows there's not much time left. Just imagine observatories everywhere, buzzing with activity. Think about the control rooms at Keck on Mauna Kea, 30,000 feet up, where the air is so thin that every breath reminds you you're somewhere special. Astronomers crowd around glowing monitors, watching live feeds from those giant telescopes. The world below is lost in clouds, but up there the sky is impossibly clear. Stars crowd the blackness, so bright and dense that even the pros stop for a second to just look. But not tonight. Tonight, every second is booked for 3i Atlas, tracking, measuring, hunting for clues about what this weird visitor really is. Meanwhile, down in Chile's Atacama Desert, where the air is so dry the Milky Way throws shadows, the very large telescope's mirrors swing to catch the comet. Usually time on those telescopes is planned out years ahead, not now. When something from another star system drops by, you make exceptions. Interstellar visitors don't care about paperwork. They show up when they want, and if you miss them, that's it. You don't get another shot. Based on the latest orbits, the comet swung closest to Earth in mid-December 2025, about 1.8 astronomical units away, roughly 270 million kilometers. That's almost twice the Earth-Sun distance. Sounds far, sure, but in cosmic terms, it's right next door. Close enough for even modest telescopes to pick out details. Close enough for spectroscopy to catch faint signals you'd never see otherwise. Careful observers stacking shot after shot all night can sometimes pull out features that would stay hidden at any other time. But that window, if it hasn't closed, it's closing fast. Earth keeps moving. 3i Atlas keeps heading out, speeding away from us at several kilometers a second. Every hour the gap grows, and as the distance stretches, the comet fades. Its weak light gets thinner, spread over a bigger and bigger area. Every step farther, fewer photons make it here. What you could barely spot in December gets tougher in January, and by February it's even worse. By March or April, only the biggest telescopes have a shot. By summer, it'll probably be gone for good, lost in the sea of faint stars and galaxies, just another tiny point of light among millions. Every day, 3I Atlas drifts farther from the sun. It's getting dimmer, slipping away, and honestly, it's only getting tougher to study. If we're going to clear up the mysteries, if we want real answers to all the questions this weird object has raised, we have to act fast. The window's closing like a door swinging shut in slow motion. Once it shuts, that's it. In a few months, only the biggest telescopes will have a shot at spotting it. By the middle of 2026, it'll fade so much that, for most of us, it's gone, lost in deep space, heading back out into the vastness between the stars. And when it finally vanishes, it'll take its secrets with it. We're only just starting to figure out what to ask, let alone what the answers are. The pressure's real, and nobody feels it more than the scientists who have spent years chasing these rare visitors. For them, 3I Atlas isn't just a cool curiosity. It's a once-in-a-career shot. Most astronomers never get to see an interstellar object pass through our solar system while they're still working. The fact that we've spotted 3 in less than 10 years, that's wild. Sure, it probably comes down to better surveys and smarter detection tools, not some sudden uptick in alien visitors. Even so, chances like this don't come often, and ones that stir up this much debate with images this wild and data this weird, those are even rarer. Astronomers everywhere get it. They feel the urgency. Telescopes on the ground, from the States to Europe, Chile to Australia, are grabbing every chance they can between bad weather and packed schedules. Space telescopes, even with their own priorities and tight calendars, are squeezing in time to follow up. Heck, even spacecraft cruising the inner solar system, built for totally different jobs, are getting in on the action when their instruments are free. The mission right now is to nail down the basics. How big is the nucleus really? What's its shape? Is it spinning? What's it made of? But underneath all that, there's a bigger reason driving everyone. What is this thing telling us about the universe outside our solar system? Is it a typical interstellar comet, or is it some total oddball we'll never see again? Are interstellar visitors usually processed? Their surfaces changed by millions of years getting blasted by cosmic rays? Or is 3I Atlas just something else entirely? These questions matter. Because 3I Atlas isn't going to be the last one we spot. Our surveys keep getting sharper, telescopes keep getting more sensitive, and machine learning is cranking detection up to a new level. In the next few decades, we'll probably catch dozens, maybe even hundreds of these interstellar objects passing through. Each one will teach us something new, help us figure out what's normal, what's strange, and what needs a closer look. But right now, it's all about 3I Atlas. This is the one we can really dig into. It's the one forcing us to face the limits of what we know, and what we don't. If we don't squeeze every bit of info out of it before it disappears, we're blowing a chance that might not come again for decades, maybe even longer. Right now, one of the top priorities is figuring out the nucleus itself. All we're seeing at the moment is the coma, the cloud of gas and dust hiding whatever solid core is inside. If we could just get a direct look at the nucleus, we'd finally know its true size, its shape, and what the surface looks like. That would narrow down the mass, the density, and what it's actually made of. Plus, we'd find out if the nucleus is a solid chunk or just a loose pile of rubble, which changes how it reacts to heat and outgassing. Big ground-based telescopes with adaptive optics are on it, fighting through atmospheric blurring to catch brightness changes that might reveal rotation or a weird shape. They're also scanning for signs of breakups or little satellites, bits that might have split off. There's a full-on, multi-wavelength campaign happening, too. Optical telescopes map out the visible structure and dust. Infrared observations, think James Webb Space Telescope, dig into the chemistry of the gases and ices. Ultraviolet telescopes catch emissions from water and other stuff boiling off. Put all this together, and scientists can start piecing together what 3I Atlas is made of, and how it's behaving, right now, as it races away from us. One of the big things astronomers watch is non-gravitational acceleration. When a comet gets close to the sun and starts outgassing, those jets of gas actually push on the comet's nucleus. The forces are tiny, but over time, they add up and nudge the comet off its purely gravitational path. So, scientists predict the orbit using only gravity, then compare it to where the comet actually shows up. Any differences give away those extra pushes. For a typical comet, these accelerations track with outgassing. They ramp up when the comet is close to the sun and slow down as it moves away. The rotation of the nucleus changes the direction and pace of outgassing, so you see the acceleration shift as the comet spins. Once the comet heads farther out and its activity drops, those accelerations fade. If that pattern gets broken, if the acceleration sticks around for too long, stays constant, or just doesn't match the outgassing, then something weird is going on. That would mean something besides sublimation is messing with the orbit. So far, nothing out of the ordinary has turned up. The data is still coming in though, and researchers are going over it with a fine-tooth comb. They're also running polarimetric studies. There's this strange negative polarization branch that showed up before perihelion, and people want to know if it sticks around or shifts as the comet gets farther from the sun and the coma thins out. Polarization tells you about the dust, its size, shape, what it's made of, so watching how it changes can reveal if the dust is just from the surface or from deeper, untouched layers. If the polarization suddenly changes, it could mean the comet's crust is peeling away, exposing brand new material underneath. The coma and tail are under the microscope too. Scientists are hunting for jets, antitails, or any weird shapes that might show where the comet's most active. They're tracking how bright it gets over time, looking for repeating patterns that would point to the nucleus spinning. They're mapping out the gases, like carbon dioxide and water, to see if they all come from the same spot or different regions. Every detail helps them pin down what's really happening with the nucleus. But what would it actually take to break the comet model? What would make scientists stop and say, "Hold on, this doesn't add up"? Here, what would raise eyebrows? First, if the comet keeps accelerating without losing enough mass to explain it, something else is doing the pushing. Second, if the nucleus turns out to be perfectly smooth or symmetrical and stays that way, that's just not how comets form. They're supposed to be lumpy and battered. Third, if the spectra show emissions from metals or chemicals that shouldn't exist in a comet, that's a red flag. Then there's thermal emission. If the comet is way hotter or colder than it should be, maybe it has an internal heat source or some strange material. Finally, if it's blasting out gas like crazy but never shows any signs of breaking up or eroding, that's odd. Either it's way stronger than any comet we know, or it's not a comet at all. None of these smoking guns have shown up yet. But the important word is yet. The observation campaign is still going, and new data comes in all the time. If anything strange does appear, someone will catch it. The problem is, 3I Atlas is fatting fast as it heads out of the solar system. By early 2026, it might be too faint for anyone but the biggest telescopes to spot. If the data quality drops off before we get answers, we might lose our shot at understanding what this thing really is. There's one more wild card, a long shot but you never know. If someone picks up radio signals, regular pulses, or anything structured that can't be explained by nature, that would change everything. The SETI folks are listening just in case. If 3I Atlas is broadcasting, someone will hear it. But if they don't, it doesn't mean much. Maybe it's just quiet, or maybe it was never meant to talk. Whatever 3I Atlas turns out to be, an oddball comet, a relic from another star system, or something stranger, documenting it matters. This is probably our best shot in decades, maybe centuries, to study an interstellar visitor up close. Who knows when the next one will show up? Maybe not for another 50 years. Maybe the next one won't even be bright enough to see. Right now, this is our moment. Let's zoom out for a second. Why does any of this matter? Why should you care about some icy, rocky thing drifting across the solar system? Here's the thing. 3I Atlas isn't just another comet. This is an interstellar visitor, a messenger from another sun. Every weird little detail we find is a clue about what's out there, beyond our own solar system. This object keeps reminding us that our ideas are too simple, that the galaxy's small bodies are way more diverse than we thought, and that the universe is a lot stranger than we give it credit for. 3I Atlas is forcing us to expand our mental boxes. For years, we've sorted the solar system's small stuff into two groups, comets and asteroids. Comets are icy and active, born in the cold outskirts. Asteroids are rocky, pretty boring, and come from the inner zones, nice and tidy. But these interstellar objects, they don't fit. They formed somewhere else, under conditions we can only guess at, circling some other star. Then they spent millions, maybe billions of years drifting through interstellar space, soaking up cosmic rays, colliding with dust, and who knows what else. By the time they get here, they aren't untouched relics from their home systems. They've changed. Their journeys have reworked them in ways we're just starting to figure out. If the idea about cosmic ray processing holds up, and honestly it looks like it does, then 3I Atlas isn't a regular comet or asteroid. It's something new, an altered interstellar traveler. And if we found one, there are probably countless more out there. Stars build planets, planets toss stuff out, and some of it ends up lost in the dark, getting baked by radiation until it wanders into a place like ours. Turns out, these visitors might not be rare at all. We just didn't have the tools to spot them until now. The science here is huge. Studying 3I Atlas lets us peek into planet and solar system formation in other corners of the galaxy. What's in its ice? How many volatiles? Are there organics? All of that tells us about the place it came from. Was there a lot of water? Did carbon dioxide hold up better? How hot or cold did it get? What kind of chemistry was going on? Our solar system can't answer those questions alone. It's just one example. Interstellar objects give us something to compare, so we can start to see the bigger picture. Then there's the whole cosmic radiation angle. 3I Atlas basically offers a lab for studying what happens to stuff after ages of exposure to galactic cosmic rays, something we could never recreate on Earth. The chemistry, the dust, the changed ices, they're records of that long journey. If we can read them, we'll learn about the space between stars, radiation out there, and how matter changes over cosmic time. That knowledge shapes our understanding of everything from how stars form to how life might start, because the same processes that shape these objects also shape the molecules that end up on planets and maybe spark biology. And honestly, it's hard not to get a little philosophical. What does it mean if we start finding and cataloging objects from other star systems, with chemistries and stories we never expected? It shifts how we see ourselves. We realize the solar system isn't the model for everything. It's just one weird little place among billions. The ice in 3I Atlas formed around a star we'll never see, in a system we'll never visit, under conditions we can only imagine. Yet here it is, sweeping by our neighborhood, close enough for us to study. That's humbling, and honestly it's pretty thrilling. The future of astronomy feels electric right now. Everything's moving fast, and the odds are finally tilting our way. It's not just about bigger telescopes or fancier detectors, though those help. What's really happening is a complete shift in how we look at the sky, how we crunch the numbers, even how we frame our questions. Take the Vera C. Rubin Observatory in Chile. It's almost ready to go, and it's about to change the game for ground-based surveys. Rubin isn't just another telescope. It's more like a time machine for astronomers. Every few nights, it'll snap photos of the whole visible sky, then compare them to catch anything that moved or changed. Asteroids, comets, exploding stars, you name it. If something suddenly appears, shifts its spot, or changes brightness, Rubin's system flags it automatically. The amount of data it'll collect is nuts. 15 terabytes every single night, year after year. No group of people could sort through all that by hand, so we're leaning on machine learning to sift the pile, pick out new candidates, sort them, and flag anything weird for a closer look. Once Rubin's up and running, we're expecting thousands of new solar system discoveries every year. Some of those will be interstellar objects, random visitors from other star systems. With Rubin's sensitivity, we'll probably spot several of those each year, which is wild compared to what used to be possible. Then you've got space telescopes like James Webb and the soon-to-launch Nancy Grace Roman Space Telescope. Webb's giant mirror and infrared eyes let it see through cosmic dust and pick up the chemical fingerprints of ices and organics, distances where regular telescopes just see fuzz. Roman's being built for big-picture stuff like cosmology and exoplanets, but its wide field and sharp detectors will make it a powerhouse for tracking solar system objects too. Looking ahead, some of the most exciting missions are still just blueprints at NASA and other agencies. People are dreaming up spacecraft that can launch on short notice, chase down interstellar objects, and fly alongside them for weeks or months. Imagine a probe matching speeds with a comet from another star system, snapping close-ups, sampling its glowing coma, and measuring things we could never study from Earth. That's not science fiction anymore. The tech is either ready or just about there, especially for objects that come close enough for a quick intercept. The hard part isn't the physics. It's all the planning, the funding, and having the hardware on standby for when the next visitor pops up. We're heading into a time when interstellar visitors won't just be rare newsmakers that everyone forgets a week later. They'll become a regular part of the conversation in planetary science. Over the next few decades, we'll probably catalog dozens, maybe hundreds of these objects. Each one will have its own backstory, its own chemistry, its own odyssey across the galaxy. Some will be icy like Borisov or Atlas. Others will be rocky, asteroid-like. And sometimes we'll meet truly bizarre outliers, think Oumuamua, that don't fit any easy box and force us to rethink what we know. Every one of these visitors carries clues about where it came from, how it formed, and what it's been through on its journey across light years of space. Bit by bit, we're building up a census of the galaxy's small wanderers. And as that list grows, it'll teach us not just about distant stars, but about where we fit into this big, tangled ecosystem we call the galaxy. 3I Atlas might be the first of a new wave, or maybe it'll just stay an outlier, a strange visitor that refuses to fit any box, no matter how many new arrivals come along. But the truth is, it's already shaken things up. Scientists have had to face the hard limits of their old models and start drawing up new ways to think about objects that don't play by the usual rules. And it's grabbed the public's attention in a way that dense research papers never could. There's something powerful about seeing structure where you expect chaos, or realizing that someone's backyard telescope might reveal a secret the big leagues missed. It's got people talking, pros, amateurs, teachers, science lovers, anyone who's ever looked up and wondered what's out there, if we're alone, or what those strange lights are drifting across the night. Really, 3I Atlas is a sharp reminder that space isn't empty. The galaxy is messy, full of debris, travelers, and surprises. And sometimes, the biggest discoveries don't start with billion-dollar missions or official launches. They start with someone, curious and stubborn, pointing a telescope at the sky and spotting something that shouldn't be there, at least according to everything they've ever learned. If 3I Atlas teaches us anything, it's humility. We like to think we've got comets figured out. We think we know what interstellar visitors should look like. But every time we put those ideas to the test, the universe throws us a curveball, something new, something we didn't see coming, something that makes us rethink what we thought we knew. That's how science moves forward, not by confirming old beliefs, but by running straight into the unexpected. And 3I Atlas delivered that jolt in style. That first blurry backyard photo, structure where there should have been a smear, became a perfect symbol for the challenge it brings. It's an image that doesn't fit, that won't let us look away, that makes us ask if we're really seeing what's there or just what we expect. Maybe the structure is real. Maybe it's just a trick of the camera. Maybe the truth is tangled up somewhere in between. But the real value is in the question. It pushes us to dig deeper, question our habits, and admit that, yeah, we could be wrong. Now, as 3I Atlas drifts away, fading into the dark, we're left with more questions than answers. What was it really? Just a worn-down comet, its surface battered by cosmic radiation for ages? A chunk from some alien planetary system so weird our chemistry books can't explain it, or something completely off our radar. Maybe we'll never pin it down. The observation window is slamming shut. Our data is patchy. The experts are still arguing. And yet that discomfort, the not knowing, is kind of a gift. It reminds us the universe doesn't owe us any easy answers. Some mysteries might sit unsolved for decades, maybe centuries. And the hunt for those answers matters, even when they slip through our fingers. In the end, 3i Atlas reminds us we're just getting started. We've barely begun to count all the strange things out there. Our tools and theories are still catching up. Every weird visitor, every offbeat observation, every photo that breaks the pattern, it's all part of the story. Each one moves us a little closer to seeing the bigger picture, one piece at a time. Here's the thing, I have one last question for you, and it's the kind that sticks with you after the words fade out. When the next visitor from the stars shows up, and it will, are we going to spot it? Or will it just slip by, invisible, because it doesn't match what we expected? Maybe it'll look too weird, or too pristine, or just off. 3i Atlas pushed us to look closer, to question everything, to not cling so tightly to what we think we know. The universe doesn't care about our comfort zones. It doesn't owe us answers we recognize. Sometimes the messenger is the message. Sometimes the universe just wants to remind us, you don't have it all figured out. So stay curious, stay skeptical, keep watching the sky, because the next thing that shouldn't be possible is almost here. Whether we're ready or not, the cosmos keeps tossing us clues, sending us puzzles, daring us to stretch past what we think we understand. 3i Atlas isn't the end of the story. It's a page, maybe a paragraph. More chapters are coming. The real question is, will we be open enough, curious enough, humble enough to notice them when they arrive? Think about it. A backyard telescope spotted something. The big professional observatory saw something else. Both observations are real, both matter. And somewhere between those two glimpses is a truth we're still trying to wrap our minds around. Whatever that truth turns out to be, it's worth waiting for. It's worth the not knowing. It's worth every late-night skywatch, every blurry image, every stubborn question. Because that's what science really is. A bunch of humans reaching for clarity, hungry for deeper understanding, refusing to stop asking, what else? There's something deeply human about how we face the unknown. We bounce between awe and anxiety, between wanting to understand and wanting to stick with what feels safe. 3i Atlas brought all that out in a way few space stories have in recent memory. Part of it is that wild photo from Paul Craig's, structure where we expected just a smudge. Part of it is the timing. Right as talk about extraterrestrial life is suddenly mainstream, with officials admitting there are things up there we can't explain, and looking for life beyond Earth is starting to feel less like a fantasy and more like an overdue discovery. And honestly, part of it is just the fact that we're dealing with a visitor from another star, a messenger from somewhere we can't go, carrying secrets we can only guess at. But zoom out from the technical debates, polarimetric signatures, weird compositions, real or fake backyard photos, and there's a bigger story unfolding. We're learning bit by bit to see ourselves not as the center of everything, not as special or alone, but as one tiny piece of a sprawling cosmic puzzle. This isn't a brand new idea. Copernicus told us long ago that Earth isn't the center. Darwin showed we're part of the same story as every other living thing. Modern cosmology. It's hammered home just how many galaxies are out there, how many stars, how unlikely it is that we're the only ones. But knowing that in your head is one thing, feeling it, getting it deep down, that's different. And these interstellar visitors do something the numbers can't. They make the vastness real. You can point a telescope at something that came from another star. You can see it, measure it, argue about it, and suddenly the universe isn't just big. It's right here in front of us, waiting for us to notice. When you see an image of 3i Atlas, read about what it's made of, or follow its strange path through space, you're not just staring at some random comet, or whatever it turns out to be. You're looking at evidence that the galaxy isn't empty. Planetary systems out there are forming, changing, and tossing pieces of themselves out into the void. Some of that stuff drifts for millions of years before it finds a new home, maybe even our own solar system. It's a reminder, we're not cut off or living in some isolated bubble. Material and energy swirl around, connecting stars and planets and all the chaotic creative processes that fill the universe. If matter from other star systems can end up here, and our own can end up out there, then the idea of a strict boundary between our solar system and theirs starts to blur. Really, we're all just part of the same cosmic story, the same wild experiment in physics, chemistry, and maybe, someday, biology. This shift in perspective sneaks up on you, but it's huge. It changes how you think about where we come from. The water in the oceans, the carbon in your body, the nitrogen in the air. Where did all that start? Some of it formed right here, in the cloud of gas and dust that became the sun and its planets 4.6 billion years ago. But some of it arrived later, delivered by comets and asteroids that formed way out in the cold, then wandered inward and smashed into the young Earth, dropping off water, organics, and other goodies. And a few of those visitors might have carried material that didn't even start here. Dust and ices from beyond our solar system, maybe captured from passing clouds, maybe hitching a ride on objects like 3I Atlas as they drifted by during planet formation. So yeah, there's a real chance that some part of you, some atoms in your body, once circled a different star, traveled across interstellar space, mixed into the solar nebula, became part of a planetesimal, crashed into Earth, and eventually ended up inside you. That's not poetry, that's physics. Interstellar objects like 3I Atlas aren't just oddities. They're direct links to our cosmic past, reminders that everything in the universe is tangled together in ways we're only starting to understand. And then there's the question nobody wants to ask out loud. What if some interstellar objects are more than just rocks and ice? This is where things get weird, and a lot of scientists get uncomfortable, because now you're drifting into territory that sounds like sci-fi, or maybe even conspiracy theory. But it's a real question, and lately, serious researchers are actually starting to talk about it. If intelligent life isn't rare, if even a handful of civilizations out there manage to leave their home planets and explore, then the galaxy should be littered with their artifacts. Not necessarily spaceships whipping past at light speed, though who knows, but probes, satellites, long-dead instruments, or just the debris from ancient missions by civilizations that might not be around anymore. Some of that could pass through our solar system. If interstellar exploration happens at all, it'd honestly be strange if nothing artificial ever drifted by. Trying to tell apart something artificial from something natural is tougher than it sounds. When we picture an interstellar probe, we usually default to big, shiny machines, metal hulls, blinking lights, antennas. Basically, every sci-fi movie rolled into one. But real probes, especially ones built for million-year journeys, probably don't look anything like that. They're more likely small, maybe just a few meters wide, maybe even less. Lighter is better if you want to make the most of your propulsion. And forget the shiny surfaces. In deep space, anything reflective gets sandblasted and fades. So you end up with something dark, hard to spot, maybe on purpose or just because space is unforgiving. Most of the time, these things would probably just drift quietly, saving power, waking up only if they stumble across something interesting, like a solar system with planets that might support life. And if you really want to avoid attention, you build your probe to blend in. Use materials that mimic rocks or ice, hide any signs of tech, and just slip through unnoticed. Honestly, the perfect interstellar probe might look exactly like a comet or an asteroid. Nothing about it would jump out unless you really dig through the data and catch some little detail that doesn't fit. This isn't just some wild guess. If we were building probes to explore the galaxy, we'd make them stealthy and tough, machines that could handle centuries or millennia alone, no repairs, no contact with home. They'd have to decide for themselves what's worth investigating, what's safe, when to power up, when to play dead. And we'd have to accept that most would slip by without anyone ever noticing. They'd just watch, record, maybe send a message home, and then move on, invisible to whoever's out there. If that's how we do it, why assume aliens would go for anything flashier? The uncomfortable truth is that some of the rocks and ice balls we catalog as comets or asteroids could actually be probes, and we'd never know unless we really start paying attention, setting up tests to separate the natural from the artificial, and actually applying them every time we spot something new. Take 3I Atlas. It doesn't set off any alarms. No weird signals, no unexplained movements, nothing that screams alien tech. But people are still asking the question. Not just in internet forums either. Scientists are publishing papers, talking about it at conferences. The conversation has changed. We're not rolling our eyes at the idea of interstellar artifacts anymore. Now we're building ways to look for them, deciding how to handle the evidence, figuring out what to do if we ever find something that really doesn't fit. And honestly, weird objects like 3I Atlas are forcing us to get our act together, to think hard about what an artificial visitor would actually look like, and how we'd spot it among the hundreds of natural objects we see flying by every year. Here, the funny part. The more we study natural interstellar stuff, the stranger it gets. Just floating through the cosmos, cosmic rays can turn a fresh comet into something that looks nothing like what we expect. Every planetary system out there forms in its own weird way, with its own mix of chemicals. So you end up with objects that break all the rules we learned from our own solar system. Nature is bizarre enough that we don't need to bring aliens into the picture to explain most of what we see. But that same weirdness makes it even harder to spot something artificial. We can't just say, this is too strange to be natural, because honestly, strange is normal now. If you want to claim something is artificial, you need incredible evidence. The bar is set sky high, as it should be. Still, people are asking the tough questions. We're building the tools, and we're taking the possibility seriously in a way that just didn't happen 10 years ago. So here we are again, staring at that image, Paul Craig's backyard telescope shot. The one with the odd structure, the picture that kicked off this whole conversation. Is it real or just a glitch? Honestly, no one knows yet. Maybe we'll never know unless someone else catches the same thing with different gear, different software, or unless 3I Atlas does something so strange in the future that there's no way to explain it away. Still, whether the image turns out to be a fluke or the real deal, it's done something important. It's made people pay attention. It's sparked arguments. It's pushed both pros and hobbyists to take a closer look, to challenge what they thought they knew, to dig deeper into the data. It's a good reminder. Observing isn't just about pointing a camera and recording what's there. Every tool, every method shapes what we see. The truth is messier than any single picture or dataset can show. And honestly, that blurry, debated photo hints at what astronomy's future might look like. Imagine a world where backyard astronomers and professionals work side by side, where someone with a modest telescope can actually move the field forward, where the tools for discovery aren't locked behind a paywall or a university badge. We're living in an amazing time for this stuff. Telescopes that once cost as much as a car now go for a few $100. Cameras and image processing software are everywhere, not just in research labs. Online forums are full of people swapping tips, sharing data, arguing late into the night. It's a wave of collaboration and curiosity that cuts across the old boundaries. Mysterious objects like 3I Atlas give these communities a real puzzle to chew on, questions that matter, discoveries that could actually shift how we see the universe. But the story isn't over. Sure, the window for observing 3I Atlas is closing, but the work goes on. People are poring over the data. New papers are coming out. Models get tweaked, theories get tested with fresh observations. And somewhere out there, drifting through the dark between the stars, more interstellar visitors are already on their way. Some of them will be familiar, nothing wild. Others, they'll be as strange as 3I Atlas, forcing us to stretch our categories and rethink what we thought we understood. And maybe just once something will show up that's so far outside the lines we have to go back and redraw them from scratch. If that ever happens, we'd better be ready to watch closely, to ask tough questions, to follow the evidence even if it drags us somewhere uncomfortable. Above all, to stay humble. The universe is bigger, weirder, and more full of surprises than we'll ever guess. So we keep watching. We wait. We line up our telescopes, amateurs and professionals together, searching for the next oddball, the next mystery, the next thing that blows open our idea of what's possible. That's what real exploration looks like. It's not just rockets and probes flying off to distant worlds, though that's part of it. It's every tool we've got: telescopes, cameras, algorithms, and most of all, people who are willing to look at the data and ask, what am I seeing? Science isn't a finish line. It's a way to live, a mix of curiosity, skepticism, and flat-out wonder. Whatever 3i Atlas ends up being, it's a perfect example. Something that doesn't fit, an observation that shakes up our models, a single image that gets everyone talking. Maybe we'll never crack the mystery, but honestly, that's where the magic happens. In the not knowing, in the arguments and uncertainty, that's where knowledge grows. That's where science lives. That's how we learn the universe doesn't owe us easy answers. But with patience, rigor, and a little creativity, we can still piece together the story, one mystery at a time. And the questions keep coming. Is 3i Atlas a process comet? Pretty much, yeah, at least in part. But is that the whole story? Probably not. There's always more to dig into. Will we ever know everything? Unlikely. Still, the chase goes on. As long as there are people pointing telescopes skyward, as long as curiosity keeps us asking what that moving speck really is, we'll keep searching, we'll keep learning, and we'll keep getting surprised. That's just what humans do in a universe this massive and this weird. We're the species that looks up, that wants to know why, and every so often manages to find answers. 3i Atlas is just another step in this never-ending journey. A weird step, sure, maybe a shaky one, but it's a step forward all the same, toward a future where we understand a bit more, see a bit farther, and figure out our place in the cosmos with a little more humility and awe. The backyard astronomer saw one thing. The professionals saw another, and somewhere between those sightings, buried in the data, the arguments, and the mysteries, there's a truth we're still learning to spot. Chasing that truth matters. It always has. It always will. There's something about the night sky that knocks us down to size. Just standing under the stars, away from the glare of cities, you see the Milky Way stretched out above you, a glowing river across the darkness. Sure, you notice thousands of stars, but that shine is the combined light of billions more, too faint and far to pick out one by one. To ancient eyes, it was a road, or a river, or maybe a crack in the sky where the gods let their light spill through. We know more now. It's our galaxy's disk, seen edge-on, a spiral of stars, gas, and dust circling a supermassive black hole at the center. Most of the stars we spot are our close neighbors, just a few hundred or thousand light years away, tucked inside a galaxy that stretches 100,000 light years across. And beyond our galaxy, billions more galaxies, each packed with billions of stars, reaching all the way to the edge of the observable universe, 46 billion light years out in every direction. The numbers get so big, they almost stop making sense. But then something like 3i Atlas shows up and makes it all feel real. Here's an object, an actual chunk of stuff, that came together around one of those far-off stars, one of those distant pinpricks in someone else's sky. It formed out of gas and dust in some protoplanetary disk, maybe 4 or 5 billion years ago, maybe more recently. We don't know. Maybe it was part of a solar system like ours, with rocky planets near the star and gas giants farther out. Or maybe it came from someplace totally unfamiliar. At some point, something knocked it loose. A close call with a giant planet, a near miss with another star, or just slow, steady changes over millions of years. Whatever happened, it got flung out, speeding away from its home star for good. And then it wandered. How long? We can only guess. If it started near a star just tens of light years away and moved at the usual comet pace, it's been adrift for tens of millions of years. If it set out from farther, maybe hundreds of millions. All that time, it stayed alone in a way that's hard to picture. Unbound, not circling anything, just drifting through the emptiness between stars. Cosmic rays hit it non-stop. Sometimes it cruised through clouds of interstellar gas and dust. It was colder than anything here on Earth. Darker, too, darker than any cave, any night you've ever known. It showed up in our solar system almost out of nowhere. The sun's gravity caught it, dragging it in faster and faster, giving it just a brief chance to streak past the one place in the universe where someone might actually notice. And we did notice. We scrambled to aim our telescopes, collecting its faint light photon by photon. From those tiny signals, we pieced together its path, guessed at its makeup, tried to understand what it was. Now it's already on its way out, slipping back into interstellar space. Odds are, we'll never see it again. Its orbit isn't coming back. It's a one-way ticket out of the solar system, off to wander the galaxy forever, unless it crashes into something else or gets swallowed by the galactic core. The chance that any other intelligent life will spot it is practically zero. We might be the only ones who ever knew it passed by. That's wild to think about. This mysterious object, full of secrets we'll probably never solve, showed itself here just long enough for us to catch a glimpse, and then it disappeared. We got lucky, honestly. Luckier still that we even had the tools to study it as it flew past. And maybe, if that backyard photo really shows what it claims, if its details are real and not just camera tricks, we're lucky in ways we won't even understand for years. Just stop and think about how unlikely all this is. There are at least 100 billion stars in the galaxy, maybe 4 times that, depending on who you ask. Most of them have planets. We know that now, thanks to exoplanet surveys. And when these systems form, they throw out tons of leftovers, chunks of rock and ice that never became planets, tossed out by gravitational chaos. If even a tiny slice of those leftovers end up flung into interstellar space, the galaxy must be crawling with them. Billions, probably trillions, of stray objects drifting through the dark. The gaps between stars are enormous. Take the distance from the Sun to the nearest star, Proxima Centauri, 4.24 light-years, or about 40 trillion kilometers. If you shrank the Sun to a grain of sand, Proxima would be another grain 7 kilometers away, and everything in between would be almost nothing. Maybe a few lonely hydrogen atoms, some dust, the faint glow from other stars, but mostly emptiness. So the odds of any one of these interstellar objects actually dropping by a star system like ours, tiny. But with so many stars and so many things flying around, eventually one does. And when it's our turn, when an interstellar visitor shows up in our neighborhood, we have to make the most of it. These aren't just cosmic oddballs. They're samples, real physical pieces of other solar systems dropped right at our doorstep. They carry clues about places we can't see any other way. We can't visit other stars, not yet. The distances are just too much. The energy it would take is off the charts. Even getting to the closest stars would take tens of thousands of years with the rockets we have now, and we're nowhere near being able to keep people alive that long. Maybe someday we'll send robots if we invent new kinds of propulsion, nuclear drives, light sails, fusion engines. But even then, the trip would last decades at best. The stars are so far away that everything else in space feels close by comparison. But these interstellar objects, they come to us. We don't have to chase them down. When they sweep through the inner solar system, close enough for us to watch, they bring pieces of their home systems with them. They hold stories about how planets form under conditions we've never seen. Every single one is like a sample return mission we didn't have to launch, a gift from the galaxy itself, for anyone curious enough to take a good look. Interstellar objects are incredible, sure, but they're also maddening. They just show up, no warning, no heads up, nothing. They don't bother to slow down or hang around for us. Most of the time, they whip past Earth on distant paths, barely visible, and spotting them takes big telescopes and a lot of patience. By the time we realize one's there, it's already slipping away, vanishing back into the dark between the stars. We get a single shot. One quick pass to grab whatever data we can before it's gone for good. That kind of pressure, it's intense. It's easy to mess up, miss something, or argue about what's most important. When you've got limited time and resources, scientists have to make tough calls. What to look at, what to measure, which questions to chase. And those calls depend on their own guesses, their models, their gut sense of what the object is and how it'll behave. If they guess wrong, if the object throws a curveball, they might miss what really matters. Sometimes they process the data in ways that hide the weird stuff. or they brush off oddities as mistakes when really those quirks might be the whole story. That's the background for the 3-Eye Atlas debate. The pros, following their usual playbook and squeezed for time, decided this thing was a comet, maybe an oddball, but still a comet. They focused on spectroscopy, chemistry, signs of outgassing. And honestly, they did a good job. We learned a lot about what 3-Eye Atlas is made of and how it stacks up against other comets and interstellar visitors. But maybe, just maybe, they missed something, a detail that doesn't fit the comet mold, because they weren't looking for it. Meanwhile, amateur astronomers working with different gear and different goals tweaked their images to show structure, to highlight edges, to pull out features the pros overlooked or ignored. One of them, Paul Craig's, snapped a photo that hints this object might be stranger than anyone thought. Is that image real? Nobody knows yet. But the fact that it exists, that it shows something unexpected, is valuable. It pushes us to ask new questions. It pokes holes in our confidence. It's a reminder that seeing things as they really are, without the comfort of our expectations, isn't easy. This is what science is all about. You look, you build an idea to explain what you see, you make predictions, you check if you're right, and if you're not, you go back and fix your model. It's a loop, and it only works if you let the evidence shake up your assumptions. The catch: people are wired to see patterns. We spot what we expect, and we force new stuff to fit into old boxes. That's not a bug, it's how we survive in a messy world. But it means we sometimes miss the stuff that doesn't fit, those oddities that could change everything. That's why we need all kinds of perspectives. Professionals, amateurs, people with different tools and questions. The more angles we have, the better our chances of seeing what's really out there, not just what we want to see. That's how we keep from getting stuck, and sometimes that's how we discover something new. 3-Eye Atlas is shaking things up. Its weird mix of features and baffling structure are pushing astronomers, pros and amateurs alike, to wrestle with the limits of their theories and face the blind spots in what they've seen so far. People are arguing, which is honestly the best thing that can happen. Some say it's just an oddball comet, nothing more. Others see hints of something stranger, something that needs a brand new explanation. Both sides matter. Both help us get closer to what this thing actually is. And in the end, it's not about who sounds more convincing or how many people agree. The answer comes from the evidence, careful, detailed observations that finally settle the debate. We might not get those crystal clear observations for 3-Eye Atlas. Time's running out. But the real value is in the questions we're asking now, the methods we're sharpening. Those will stick with us for the next interstellar visitor and the next after that. We're just at the start here, an era where interstellar objects become a regular part of astronomy. Every few years, another one swings by, and we get another shot at exploring the wild variety out there in the galaxy. Each one teaches us something about other stars, other planetary systems, and how unique or not our own solar system really is. And who knows, maybe watching from a distance won't be enough forever. Maybe someday we'll launch spacecraft to chase down these visitors, match speeds, fly alongside, and study them up close. Imagine landing a probe on an interstellar comet, drilling into its ice, grabbing samples and running the tests right there. Maybe we'd find organic molecules, complicated chemistry, even the building blocks of life, amino acids or nucleotide bases. Maybe we'd uncover clues in the isotopes, hints about the star where this thing was born, the swirl of the protoplanetary disk, secrets we'd never see except in these cosmic messengers. That's where interstellar object science is headed. Not just watching, but exploring, building missions to squeeze every bit of information from these rare guests, maybe even bringing souvenirs back to Earth. We can't quite do that yet, but it's coming. And when we get there, the arguments and puzzles around 3-Eye Atlas will look like baby steps, just the beginning of something much bigger. For now, we use what we have. Ground-based telescopes, space telescopes, cameras, spectrometers, clever algorithms, and a good dose of human gut feeling. Sometimes we get images like the one from Paul Craig's, strange, a little haunting, and a reminder of how much is still out there to discover. The story of 3-Eye Atlas isn't really about one object. It's about how we see, how we make sense of what we see, how we navigate the messy gap between raw data and real understanding. It's about the tools and assumptions we bring, and the humility it takes to admit when we just don't know. Sometimes observations clash and no answer fits everyone's expectations. That's not comfortable. We crave answers, some kind of closure, so we can put 3-eye atlas in a tidy box and move on. But the universe doesn't play that game. Sometimes the mysteries just keep going. And honestly, that's okay. Because the act of asking questions, sticking with the investigation even when things don't add up, that's where the real progress happens. That's how we learn. That's how we move forward piece by piece toward a deeper understanding of the universe and our place in it. Whatever 3-eye atlas turns out to be, it's already given us something valuable. A stubborn mystery, a challenge, a strange observation that refuses to fit and makes us think harder, look closer, question more deeply. That all by itself earns this odd visitor a spot in the story of astronomy, not as a final answer, but as a question. And we're still figuring out